Hello and welcome back. In the last video, I talked about Nernst equations, and in this video, let us discuss about the conductance of electrolytic solutions. So let's get started. It is necessary to define a few terms before we consider the subject of conductance of electricity to electrolytic solutions. So the first term we have is electrical resistance, which is represented by the symbol R, and it is measured in ohm, which you might be knowing by now. It can be measured with the help of a Wheatstone bridge, with which you are familiar from the study of physics. The electrical resistance of any object is directly proportional to the length L and inversely proportional to the area of cross section. So we have R proportional to L by A, and we use the proportionality constant rho, which is a Greek letter to refer to resistivity, or otherwise called specific resistance. So we get R is equal to rho L by A. The SI units are ohm meter, and quite often its submultiple ohm centimeter is also used. IUPAC recommends the use of the term resistivity over specific resistance, and hence in the rest of the video we will use the term resistivity. Even in the textbook they use the term resistivity more often than specific resistance. Physically, the resistivity for a substance is its resistance when it is 1 meter long and its area of cross section is 1 square meter. It can be seen that 1 ohm meter is equal to 100 ohm centimeter, or 1 ohm centimeter is equal to 0.01 ohms. By the way, I hope the intuition for the first definition is clear. We can obtain the definition from the equation which we've seen before, that is R is equal to rho L by A. We shift things around and we get rho is equal to R A by L. So the resistivity is the resistance when we take unit length and the cross section area as 1 square meter, so that we get rho is equal to R into A, that is 1, by L, that is 1. So we get rho is equal to R. That's the definition basically. So let's move on. The inverse of resistance is called conductance, and it is referred by G in the textbook. So I am following the same conventions. So conductance, I am going to refer it by G. So we have the relation G is equal to 1 by R, and R is equal to L by A. So G is equal to A by OL, and 1 by rho, I am going to replace it with a new term, that is kappa, and it is also a Greek word. I will talk more about it in the coming slides. Before that, the SI unit of conductance is Siemens, and it is represented by the symbol S, and it is equal to ohm inverse. By the way, MHO, mho, is also used to represent ohm inverse. It's just putting ohm other way around. Just like inverse of resistance is called conductance, the inverse of resistivity is called conductivity or specific conductance, and it is represented by the symbol kappa, which is again a Greek letter. And IUPAC has recommended the use of the conductivity over specific conductance, and hence we shall use the term conductivity in the rest of the video. The SI unit of conductivity or Siemens meter inverse. Why? Conductivity is inverse of resistivity. For resistivity, the unit is ohm meter. So 1 by ohm meter, that is ohm inverse meter inverse, which is Siemens meter inverse. So that's the unit of conductivity. But quite often kappa is expressed as Siemens centimeter inverse. That is, we are not going to use the SI unit most of the time. Conductivity of a material in Siemens meter inverse is called its conductance when it is 1 meter long and its area of cross section is 1 square meter. analogous to how we defined resistivity in terms of resistance. It may be noted that 1 Siemens centimeter inverse is equal to 100 Siemens meter inverse. The magnitude of conductivity varies a great deal and depends on the nature of the material. It also depends on the temperature and pressure at which the measurements are made. Materials are classified into conductors, insulators, and semiconductors depending on the magnitude of conductivity. You might have seen these terms earlier, I suppose, I hope so at least. So, metals and the alloys have very large conductivity and are known as conductors. Certain nonmetals like carbon black, graphite, and some organic polymers are also electronically conducting. So, what are conductors? Materials that have large conductivity. Substances like glass, ceramics, etc., have very low conductivity and they are called insulators. Substances like silicon, doped silicon, and gallium arsenide having conductivity between conductors and insulators are called semiconductors and they are important electronic materials. So, what are conductors? Large conductivity. Insulators, very low conductivity, and semiconductors, intermediate, like they come between conductors and insulators. Their conductivity comes in between these two materials. Certain materials called superconductors by definition have zero resistivity or infinite conductivity. So that's the classification of materials. Electrical conductance to metals is called metallic or electronic conductance. This electronic conductance is due to the movement of electrons. The electronic conductance depends on 1. The nature and structure of the metal, 2. The number of valence electrons per atom, 3. Temperature. It decreases with increase in temperature. Do note these 3 points, that is the factors on which the electronic conductance depends upon. These are pretty important ones. What are they? The nature and structure of the metal, the number of valence electrons per atom, and temperature. As the electrons enter at one end and go to the other end, the composition of the metallic conductor remains unchanged. The mechanism of conductance to semiconductors is more complex, and you will learn that in physics. We already know from class 11 unit 7 that even very pure water has small amounts of hydrogen and hydroxyl ions, which is approximately 10 power minus 7 molar, which lend it very low conductivity. So, because of the presence of hydrogen and hydroxyl ions, it gives water very low conductivity, approximately 3.5 into 10 power minus 5 7 meter inverse. When electrolytes are dissolved in water, they furnish their own ions in the solution, hence the conductivity also increases. The conductance of electricity by ions present in a solution is called electrolytic or ionic conductance. So previously we used the term metallic conductance where the conductivity is because of electrons in the metal. Now the conductivity is because of the ions in the solution, and such electricity produced because of ions we call it electrolytic or ionic conductance. The conductivity of electrolytic solutions depends on the nature of the electrolyte added, size of the ions produced and their solvation, the nature of solvent and its viscosity, concentration of the electrolyte, and finally the temperature. It increases with increase in temperature. So these are the 5 factors on which electrolytic conductance depends upon. Now let's see how to measure conductivity of ionic solutions. We know that accurate measurement of an unknown resistance can be performed on a Wheatstone bridge. You should have seen that in physics. However, for measuring the resistance of an ionic solution, we face two problems. What are they? Firstly, passing direct current changes the composition of the solution. Secondly, a solution cannot be connected to a bridge like a metallic wire or other solid conductor. So these are the two problems that we have, because of which we cannot find the resistance of ionic solution easily. The first difficulty is resolved by using an alternating current source of power. So the problem was because of DC we had a problem, so we are going to just make it AC, that is an alternative current, and that solves the first problem. The second problem is solved by using a specially designed vessel called conductivity cell. So now we will learn about these conductivity cells in detail, but before that, these are two different types of conductivity cells, and do note that the electrodes are platinum. Yeah, so let's move on. The images are there in your textbook. Basically, it consists of two platinum electrodes coated with platinum black, that is finely divided metallic platinum is deposited on the electrodes electrochemically. These have area of cross section equal to A and are separated by a distance L. Therefore, solution confined between these electrodes is a column of length L and area of cross section A. The resistance of such a column of solution is then given by the equation R is equal to rho L by A, that is L by kappa A. Notice that it is L and not 1, so don't get confused like me now. So we have seen this expression in the first slide, and this is a pretty simple one. You might have seen it in your lower classes. R is equal to rho L by A, which is equal to L by kappa A. So the quantity L by A is called cell constant and it is denoted by G star. Do note that it is L and not 1, it is L by A. It depends on the distance between the electrodes and the area of cross section. Since G star is L by A, it has L and A, so it should depend on the distance between electrodes, that is L, and the area of cross section, that is A. It is pretty simple to understand also. It has a dimension length inverse, which you can get it from the expression G star is equal to L by A. It can be calculated if we know L by A, again pretty simple. But measurement of L and A is not only inconsistent but also unreliable. So what can we do? Let's see. The cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl solutions whose conductivity is known accurately at various concentrations and at different temperatures. There is a table in the book, that is table 3.3. It's just a table that has various concentration and at different temperatures what's the conductivity of this KCl solution. It's just a it's just a factual thing, so I'm not going to put the table over here. You can refer to it from the book. That's table 3.3. The cell constant G star is then given by the equation G star is equal to L by A is equal to R kappa. Once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The setup for the measurement of resistance is shown at the right. It consists of two resistors, R3 and R4, a variable resistance R1, and a conductivity cell having the unknown resistance R2. The Wheatstone bridge is fed by a oscillator O at a source of AC power in the audio frequency range 550 to 5000 cycles per second. T is a suitable detector, a headphone or other electronic device, and the bridge is balanced when no current passes through the detector. Under these conditions, that is, when the Wheatstone bridge is balanced, unknown resistance R2 is given by R1 R4 upon R3. These days, inexpensive conductivity meters are available which can directly measure the conductance or resistance of solution in the conductivity cell. Once the cell constant and the resistance of the solution in the cell is determined, the conductivity of the solution is given by the equation kappa is equal to cell constant by R, that is equal to G star by R. The conductivity of solutions of different electrolytes in the same solvent and at a given temperature differs due to charge and the size of ions in which they dissociate, the concentration of ions, or ease with which the ions move under a potential gradient. It therefore becomes necessary to define a physically more meaningful quantity called molar conductivity, denoted by the symbol lambda m, that is capital lambda if you have not seen it before. So we denote molar conductivity with lambda m, where m is a subscript. It is related to conductivity of the solution by the equation molar conductivity, that is lambda m, is equal to kappa by C. So that's how molar conductivity and conductivity is related. Unit of lambda m is Siemens meter square mole inverse or Siemens centimeter square mole inverse. And this is the relation between Siemens meter square mole inverse and Siemens centimeter square mole inverse, that is 1 Siemens square mole inverse is equal to 10 to the power 4 Siemens centimeter square mole inverse. So now that was too much of theory. Let's solve a small question now. It's a simple question. So here's the question. I'm going to read it out fast. The resistance of a conductivity cell filled with 0.1 molar KCl solution is 100 ohm. If the resistance of the same cell when filled with 0.02 molar KCl solution is 520 ohm, calculate the conductivity and molar conductivity of 0.02 molar KCl solution. The conductivity of 0.1 molar KCl solution is 1.29 Siemens meter inverse. And just in case you are confused, molar inverse is molar, so I write it directly as molar. So you can take 10 seconds or 15 seconds to solve this problem. Then we will solve it together. And you can pause the video if you want more time. Okay, let's solve it together now. The cell constant is given by G star is equal to kappa R. We have seen this relation before. And substituting kappa as 1.29 Siemens meter inverse and R as 100 ohms, we get 129 meter inverse. So this is the cell constant. Conductivity of 0.02 molar KCl solution is G star by R, and putting the numbers 129 by 520, we get it as 0.248 Siemens meter inverse. So that's a conductivity of 0.02 molar KCl solution. The concentration is 0.02 molar. We'll convert it to mole meter per minus 3 and we get 1000 times 0.02 mole meter per minus 3, that is 20 mole per meter cube. Yeah. So now molar conductivity is simple, that is kappa by C, and substituting back the values, we have 0.248 Siemens meter inverse upon 20 mole per meter cube, that is 124 to 10 to the power minus 4 Siemens meter square mole inverse. And if you remember, this is equal to 124 Siemens centimeter square mole inverse, because 1 Siemens meter square mole inverse is 10 to the power minus 4 centimeter square mole inverse. Let's solve another question quickly. The electrical resistance of a column of 0.05 molar NaOH solution of diameter 1 cm and length 50 cm is 5.55 into 10 to the power 3 ohm. Calculate its resistivity, conductivity, and molar conductivity. You get another 15 seconds to solve it. Feel free to pause the video if you want more time, and yeah, we will solve it together after that. Okay, I think I have given you enough time, so now let's solve it together. So first let us calculate the cross section area, that is pi r square, which is 3.14 into 0.52 centimeter square, that is 0.785 centimeter square, and length is 50 centimeter. By the way, in this question I am going to use centimeters everywhere instead of meters. So now we have A and L. So we know R also. So calculating resistivity is simple. We have R is equal to L by A, which is rho is equal to RA by L, and substituting RA and L, we get resistivity as 87.135 ohm centimeters. So now we have got resistivity. Conductivity is just its inverse. So kappa is equal to 1 by rho, that is 1 by 87.135 Siemens centimeter inverse, which is 0.01148 Siemens centimeter inverse. So two parts of the question is solved. Now we have got molar conductivity to be solved. So molar conductivity, that is lambda m, is 1000 kappa by C centimeter cube liter inverse, and substituting back the values, we have molar conductivity as 229.6 Siemens centimeter square mole inverse. So I hope this question and the previous questions are clear. You should be knowing how to solve such questions. So let's move on. Let's study the variation of conductivity and molar conductivity with concentration. Both conductivity and molar conductivity changes with the concentration of electrolyte. Conductivity always decreases with increase in concentration, both for weak and strong electrolytes. This can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. The conductivity of a solution at any given concentration is the conductance of the 1 unit volume of solution kept between two platinum electrodes with unit area of cross section and at a distance of unit length. I repeat, the conductivity of a solution at any given concentration is the conductance of 1 unit volume of solution kept between two platinum electrodes with unit area of cross section and at a distance of unit length. This is clear from the equation. G is equal to kappa A by L, which is equal to kappa into 1 by 1 when A is equal to 1 and L is equal to 1, which is equal to kappa. Yeah. So now molar conductivity for solution at any given concentration is the conductance of the volume V of solution containing 1 mole of electrolyte kept between two electrodes with area of cross section A and distance of unit length. Therefore, lambda m is equal to kappa A by L, that is equal to kappa since L is equal to 1 and A is equal to V, where V is volume containing 1 mole of electrolyte. So lambda m is equal to kappa V. Molar conductivity increases with decrease in concentration. This is because the total volume V of solution containing 1 mole of electrolyte also increases. It has been found that decrease in kappa and dilution of a solution is more than compensated by increase in its volume. Physically, It means that at a given concentration, lambda m can be defined as the conductance of the electrolytic solution kept between the electrodes of a conductivity cell at unit distance but having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of the electrolyte. When concentration approaches 0, the molar conductivity is termed as limiting molar conductivity. So when the limit of concentration tends to 0, we say it limiting molar conductivity. It is represented by the symbol lambda naught m. The naught on the top represents limiting. So lambda naught m is limiting molar conductivity, and the variation in lambda m with concentration is different for strong and weak electrolytes, and it's given to the right of the screen. Notice the difference in the properties of the curve for KCl, which is a strong electrolyte, and CH3COOH, that is a weak electrolyte. You get like a straight line for KCl, and it is like 1 by x graph for CH3COOH. We will discuss why the curves are like this in the coming slides. First, we will discuss for strong electrolytes. For strong electrolytes, lambda m increases slowly with dilution and can be represented by the equation lambda m is equal to lambda naught m minus a root of c. Here a is a constant. So it can be seen from the expression that if we plot lambda m against root c, that is c raised to the half, we obtain a straight line with intercept equal to lambda naught m and slope equal to minus a. The value of constant a for given solvent and temperature depends on the type of electrolyte, that is, the charges on the cation and anion produced on the dissociation of electrolyte in the solution. Thus, NaCl, CaCl2, MgSO4 known as 112122 electrolytes. Why? If I dissociate NaCl, I get Na plus and Cl minus. CaCl2, I get Ca2 plus and Cl minus. The charge on Ca is 2, charge on Cl is 1. So I have 2, 1. For MgSO4, charge on Mg is 2 plus, charge on SO4 is 2 minus, so it's a 2, 2 electrolyte. All electrolytes of a particular type have the same value for A. So if I take NaCl, KCl, the value of A will be same. I take CaCl2, BaCl2, MgCl2, the A value will be same. Hope it's clear. Now we will study something called Coulombs Law. Coulombs examined lambda naught m values for a number of strong electrolytes and observed certain regularities. He noted that the difference in lambda naught m of the electrolytes NaX and Kx for NEX is nearly constant. For example, at 298 Kelvin, the difference in limiting molar conductivity of KCl, NaCl, difference between KBr, NaBr, the difference between Ki, Nai is approximately 23.4 Siemens centimeter square mole inverse, and all of these are pretty much same. Here we are investigating between Kx and NaX, where X we taken as Cl, Br and I. Similarly, it was also found that the difference in molar conductivity, the difference in limiting molar conductivity for NaBr and NaCl and KBr, KCl are 1.8 Siemens centimeter square mole inverse. That is, if I take NaBr, NaCl, the Na is same over here, we are changing Br and Cl, and if I take KBr and KCl, I am changing again Br and Cl, the K is same. The difference is 1.8 Siemens centimeter square mole inverse. So in the first case, we took the X as constant, we changed the metal ions, and in the second case, we are changing the halide ion and we are keeping the metal as constant, metal ion as constant. So this is what Coulombs observed, and on the basis of this observations, he stated this famous and very important Coulombs law of independent migration of ions. So this is a pretty important one and a pretty simple one too. He stated that the limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and the cation of the electrolyte. Thus, if lambda naught Na plus and lambda naught Cl minus are limiting molar conductivity of sodium and chloride ions respectively, then the limiting molar conductivity for sodium chloride is given by the equation lambda naught NaCl is nothing but lambda naught Na plus lambda naught Cl minus. And notice that I have used small lambda for individual ions. So we use small lambda to represent molar conductivity of an individual ion and small lambda naught for limiting molar conductivity of an individual ion. So for Na plus I have used small lambda naught Na plus. And do notice that this is valid only for limiting molar conductivity and not for molar conductivity. Okay, this addition is valid only for limiting molar conductivity. In general, if an electrolyte on dissociation gives V plus cations and V minus anions, then its limiting molar conductivity is given by like this. It's pretty simple, it's just a sum of whatever is coming out. So here lambda naught plus and lambda naught minus are the limiting molar conductivities of cation and anion respectively. We will do a small example, you will understand how to apply this. So now let's move on to weak electrolytes. Weak electrolytes like acetic acid have lower degree of dissociation at higher concentrations. Hence, for such electrolytes, the change in lambda M with dilution is due to the increase in the degree of dissociation and consequently the number of ions in total volume of solution that contains 1 mole of electrolyte. In such cases, lambda naught M increases steeply. We have seen that before on dilution, especially near the lower concentrations. Do you remember the curve for acetic acid? It was like a 1 by x curve. So as the concentration nears 0, we had a steep increase. Remember it? Therefore, lambda naught M cannot be obtained by extrapolation of lambda M to 0 concentration. At infinite dilution, that is concentration C tends to 0, electrolyte dissociates completely, that is alpha is equal to 1. But at such low concentration, the conductivity of solution is so low that it cannot be measured accurately. Therefore, lambda naught M for weak electrolytes is obtained by Coulombs law of independent migration of ions, which we have seen before, and we will see how it is obtained in question 4 in the upcoming slide. At any concentration C, if alpha is the degree of dissociation, then it can be approximated to the ratio of molar conductivity lambda M at the concentration C to limiting molar conductivity lambda naught M. So we have alpha is equal to lambda M by lambda naught M. Yeah, you must remember this. But we also know that for a weak electrolyte like acetic acid, we have seen in class 11 unit 7 that Ka is C alpha square by 1 minus alpha, and substituting the alpha as lambda M by lambda naught M, we have seen that before, it's there in the previous line. Substituting that alpha in this expression, we get C times lambda M by lambda naught M square upon 1 minus lambda M by lambda naught M, and this simplifies to C lambda M square by lambda naught M times lambda naught M minus lambda M. You just have to remember that alpha is lambda M by lambda naught M and Ka is equal to C alpha square upon 1 minus alpha. You can just put alpha over there, you don't have to memorize that expression at the bottom. So just have to remember these two things, alpha and Ka relation. So now what's the application of Coulombs law? Using Coulombs law of independent migration of ions, it is possible to calculate lambda naught m for any electrolyte from the individual ions molar conductivity value. I'm sorry, from I'm really sorry, I'm going to repeat this, please hear it again. Using Coulombs law of independent migration of ions, it is possible to calculate lambda naught m for any electrolyte from the limiting molar conductivity values of individual ions. I'm repeating it again, it's limiting molar conductivity which we are using for Coulombs law and not the molar conductivity. Please understand that. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know lambda naught m and lambda m at a given concentration. With this, we have come to the end of the theoretical part for this concept. Before finishing up, let us solve some small questions. Calculate lambda naught m for CaCl2 if the values of limiting molar conductivity for Ca2 plus is 119.0 Siemens centimeter square mole inverse, and for Cl minus it is 76.3 Siemens centimeter square mole inverse. Just 5 seconds from now, and I will solve it after that. Okay, let's solve it. It's a pretty simple one. From Coulombs law, we get lambda naught m CaCl2 is lambda naught of Ca2 plus twice the lambda naught of Cl minus. Why twice? Because we get 2 Cl minus upon dissociation. So we need to account for it, and we use 2 times of lambda naught Cl minus. Yeah. So if we have something like m cations and n cations, I'm sorry, if your salt or electrolyte gives m cations and n anions, it will be m times the limiting molar conductivity of cation plus n times the limiting molar conductivity of anion. Do remember that too. Yeah. So we have lambda naught Ca2 plus 2 times of lambda naught C minus, which is 119.0 plus twice 76.3 Siemens centimeter square mole inverse, which is 271.6 Siemens centimeter square mole inverse. Pretty simple, right? Now let's solve another question. Lambda naught m for NaCl, HCl and NaAC are 126.4, 425.9 and 91.0 Siemens centimeter square mole inverse respectively. Calculate the lambda naught m for HAC, that is acetic acid. So this is the application of Coulombs law, which is very important. We are going to determine the limiting molar conductivity of acetic acid, that's a weak electrolyte, by knowing the limiting molar conductivity of strong electrolytes. So this is how we are going to do it. I'm going to show the solution now. So lambda naught HAC, that's acetic acid, is equal to lambda naught of H plus lambda naught of AC minus, acetate anion. Now little mathematics, that is adding and subtracting. I get it as lambda naught H plus lambda naught Cl minus plus lambda naught AC minus lambda naught Na plus minus lambda naught Na plus minus lambda naught Cl minus. So the Cl minus and Cl minus gets cancelled, and Na plus and Na plus gets cancelled. So I'll be having lambda naught H plus lambda naught AC minus anyways, but we need this for calculation purposes. So from Coulombs law again, lambda naught H plus lambda naught Cl minus is lambda naught m of HCl, that is a limiting molar conductivity of HCl, and lambda naught AC minus lambda naught Na plus is limiting molar conductivity of NaAC, and the remaining two, that is lambda naught Na plus and lambda naught Cl minus, gives me minus limiting molar conductivity of NaCl. So putting back the values again, which is pretty simple, I get 390.5 Siemens centimeter square mole inverse, and this value is the limiting molar conductivity of acetic acid. So I hope these two questions were clear, and with this we have come to the end of this video. In this video, we discussed about the conductance of electrolytic solutions in great detail. In the next video, I would like to talk about other type of electrochemical cell known as the electrolytic cell and something known as electrolysis. I hope that the content in this video was clear and hope to see you in the next video. Goodbye.